ja läheme inglise keele ka üle. So we are speaking about homework. And showing that vortex rotates as a solid body. And now Kaspar was saying telling me how he did it. Now, what about the rest of you? Do you want me to do it here and show how it should be done?
I would like to see it, yes.
So just some of you sent me, but tell me how many of so Kaspar did not send yet, right? Or did you send? I already forgot. Kaspar did not send, right? I think sent me. Siim, you did not send, right?
I couldn't manage, yes.
All right. So let us do it here then. So we have a vortex. We have a vortex, something like that. And then we want to see, know how we want to. Okay, let make a vortex bigger. So this here, let's this be vortex. And then in this area here, we have certain omega. What is it? Outside, we have what is the zero. And then we want to know at some point what is the velocity, and to consider separately if the point is inside or when it is outside. And now if it is inside at a certain distance r, and then we have the then I am applying the circulation theorem as follows. So we have circulation along the contour of V dl must be equal to flux through the contour of omega dA. Okay, and then now a left-hand side here becomes, because of symmetry we have, so this just becomes 2 pi r multiplied by V, because dl is parallel to V and V is constant, so it becomes just 2 pi r times V. Right-hand side becomes, because omega is homogeneous, it's just product of surface with the surface area. And surface area now inside here is just omega multiplied by pi r square. And that's basically it. So now we have left-hand side and we have right-hand side. So now from this equality, we have V equals omega r divided by 2V. Is that right? 2R. No, yeah. Omega r divided by pi cancels away, 1r cancels away, divided just by 2. Now I lost my tool bar for the. Oops. a moment. Let me try to hold on. No, did I? No, open board is here. No. Why I cannot see open board? It's over open board behind. Oh, strange. Something happened with my open board. Perhaps I need to close it. Now I cannot receive the process either. So something. Let me try to launch it again. Yeah, sorry. I pause recording for the time being once I figure out what is going on. And so we have expression like that. And now what does this tell us? If we have a solid body rotating, then you know that solid body, let me write it in a different color, I guess.
Can I ask a question?
Yes, sure.
How do we exactly divide by V? It's shouldn't V just be equal to omega times R divided by 2? Where does the second V come from?
Yeah, sure. Thanks for pointing out. Sure, we don't need to have V over there. Very good. Thank you.
Okay.
Just so if we have a solid body, then in the case of solid body, rotation speed is speed and angular speed are related so that V equals omega times R, where omega is angular velocity, angular speed. This is what I know for a solid body. So from here, comparing those two, I conclude that yes, indeed it is like solid body rotation, because speed is proportional to the distance. And angular speed is half of the vorticity. Okay. Everyone happy with that?
How do we know angular speed is half of vorticity?
Sorry?
Where do we get that angular velocity is half of vorticity?
Oh, because if you look here, V is angular speed multiplied by angular speed multiplied by distance. And here we have speed is a distance multiplied by omega divided by 2. So this just means that, yeah.
But what did you then mean by when you said that I found the speed outside, not inside?
Yes, this was an arbitrary point inside the vortex. Because I assumed that this point here is inside this circle where we have omega constant. But now if we take another point which is outside, like if we take a point here somewhere, then in that case, we repeat the same calculations, but now we need to use circulation for such kind of contour. And by repeating the same thing now, most of the the derivation remains the same. We only need to modify the expression for the right-hand side. So circulation still remains 2 pi r multiplied by v, but the circulation on the flux of omega on the right hand side. Now you need to keep in mind that there is no flux in this region here. Omega is 0 here. So the total flux is only within this region here. So now our right hand side becomes omega multiplied by pi, and let this be a small a square. If this radius here is a, or was it R capital? I don't remember. Probably it was R capital. We can change it into R capital.
You had area.
Yeah. So this distance, if this from here to here, if this is R capital, then we need to multiply now in order to find the total flux. We multiply vorticity multiplied by the cross-sectional area of the whole vortex, which is pi r square. And then we can deduce now that V equals omega r square divided by 2 and r small. So now outside of the vortex, velocity goes down as 1 divided by r. So we can also plot now how V depends on distance. And so it first goes linearly up and then starts going down as a hyperbola. And what rotates as a solid body is everything which is inside the vortex, but outside it is not vortex. It's outside. It's velocity starts decreasing. So go away if you have any questions. Go ahead and ask if you have any questions. Kaspar, is it clear more or less?
I'm confused why we don't have to separately like handle the case where like small r and big r, like why?
So small r is a distance of the point at which we ask what is the speed, and a big R is the radius of the vortex. So the condition of the problem was as follows. We have a two-dimensional problem. Vorticity omega is constant inside a certain circular area with radius big R. Outside, it is 0. So that was the condition of the problem. So big R is a capital R is the radius of the area where we have a vorticity. So we can say it as a radius of the vortex. And small r is a distance of the current point from the axis. Kaspar, are you okay?
But we don't have vorticity outside of big R.
Outside vorticity is 0.
Yeah.
So if we calculate the flux, and then I need to integrate over the whole area, over the whole interior part of the green circle which we have on the screen. And so this integral comes down into 2 parts. So I can express it like that. So this integral here, this becomes now integral over the part where r is smaller than r capital omega dA, and integral over the part where r is smaller than r capital omega dA. The distance r prime is the current distance. Okay, the current distance, and then this one here is 0 because in that region where r is distance is bigger than r capital, there is a vorticity 0. Remains only the first integral, and the first integral is just omega pi r square.
I don't get like if we then yeah, if we go bigger than big R, small r goes bigger than big R, then omega is 0. But then why? But the big R is moving as a solid body. Then why would we have like decay or like decrease of like
Once again,
I don't know how to word this. Yeah, we can just move on, I think.
Okay, you can think it over. Actually, it's quite easy. So I think maybe you have some misconception of something, but try to think over. And if you have any, if you can formulate your question, then I can answer. But
on the lower right graph, can you put where big R begins?
Yeah. So in this lower right graph here, R is here. So as long as the current point is inside, the first formula applies. As long as R small is bigger than R capital, then the other formula applies. And so the other formula is actually this one here, okay? Okay? And this is pretty much if you have like maybe in atmosphere you have those big cyclones or hurricanes, how you call it in English, and then more or less it is exactly that you have in hurricane, and in the center of a big hurricane you have vorticity, and outside the speed goes down as a distance from the center.
Like, okay, I think my confusion is about omega 0 outside of big R, because if omega is 0 outside of big R, then V would be equal to 0 times R big R squared divided by 2R.
Yeah, 0 multiplied by this, I can stripe it in red, for instance. So we break this integral, which we have, into two parts, this and that that one here corresponds to integral over this region over here. Surface, it would be surface area of the right striped in right, surface area multiplied by omega, which is 0. So 0 multiplied by surface area gives 0. So this whole thing is 0. So that remains only the first term. Kaspar, how is it?
Just ask it next time in person, maybe.
Sorry?
I'll just try to ask it next time in person, maybe.
Yeah, if you manage to formulate, yeah, maybe you just, if you think it over, maybe it becomes clear as well. All right, so let's go on. Anyone else is happy and everything clear?
More or less, I guess.
Yeah, Raido, you got the same answer? I didn't check. I managed to check. So did you get the same results as me?
Yeah, I got the same for the inside, but I understood now also how it works outside, I think.
Okay. All right. Very good. Kristlin? Okay.
Yeah, I don't have any questions about.
Okay. But then we can move on, and now is the next topic, and the next topic was what we have in the lecture from last year. We had on the one hand we had stability of two-dimensional vortex. This is the first major part, and then we had instabilities, Rayleigh-Taylor and Kelvin-Helmholtz instability. So how did it go? Did you look lectures and where should I clarify and what topics?
I had a question. You had in one point Laplacian of pressure divided by density, and I didn't quite understand where that term came from.
Laplacian of pressure and
By density.
yeah, but density we assumed constant mostly, I think.
Yeah, I was just thinking, what does that term describe? One, like there's one term for the fusion, one is for advection, and then what is that term?
Can you tell me which, so during selection, which minute I have also on my other screen here, no, what now? What happened now? Accidentally touched here on the screen and oh. Oh. Again, something strange happened.
Board on the right, top right bar.
Top right bar.
Board, yeah.
Board, but this is exactly what I had.
Left.
Okay, I can trust the documents and I can try to open it again. Yeah, maybe it works that way. Okay, now I got it back.
Yeah,
I touched accidentally something and then I got to that screen. All right, so it happened because I was opening my video. And so which minute you have?
1 hour and 33 minutes.
33 minutes.
1 hour and 33.
1 hour 33.
Yeah.
It's already towards the end of it. Yeah, this is where we study Kelvin Helpsons already. So maybe just let us collect questions from everyone. So we can go to that, but maybe by going by order, maybe we have something before to discuss. Because your question is already towards the end of the lecture, but maybe some parts from the beginning. Is it everything clear from the parts before?
I don't remember where it was, but the infinitely many conservation laws part was a bit confusing. So
okay. So yeah, as a matter of fact, we don't so much use. We do use these infinitely many conservation laws, but basically we have first, if we take our underlying Navier-Stokes equation, if we neglect the viscosity mu equal to 0, then without viscosity energy is conserved. So integral rho v squared divided by 2 d cube r is constant kinetic energy. This is the first, but we don't have more. As long as if we have 3D geometry. But in 2D, we learned that we have actually equation of the motion of the fluid can be written in such a way that d omega over dt equal to 0. So which means that d over dt plus v nabla applied to omega is 0. So this means that if we have if we consider a small piece of fluid, then it evolves into something, but omega remains the same as time goes on. And now, because of that, if we consider a whole domain where flow is happening, so let us consider integral like that, arbitrary function of vorticity. And these, because now we have two-dimensional flow, so we take integral over two-dimensional space, d square r. So what happens with that integral? So initially we have certain distribution of the different values of omega at different points. Each cell, infinite small cell, has its own omega. And now, as time goes on, this grid evolves something different. For simplicity, I won't do much. I can just make it like parallelograms, like that. But if we have incompressible flow, and this is valid for incompressible flow. Incompressible flow. Now, if we have incompressible flow, so surface areas here remains the same. D square r here and here is also d square r. These are equal because we have incompressible flow. So what I draw here, I make a certain grid initially, and then I look how this initial grid evolves, like during Lagrangian transport, how these vertical and horizontal lines, what they become after fluid has been mixing to a certain degree. And then now I can, it's the same integral. Integral, you know that as long as integral converges, it doesn't matter which grid you use for integration. You can take like a rectangular grid, but you can take in polar coordinates grid like that, and whichever way everything works, right? So which result will be the same regardless of which grid you use. And in particular, if you use a rectangular grid or a parallelogram grid, the result is the same. And now, if this integral here, you can think of as a sum of over infinitesimal areas, which is a function of that function which we have of omega at I cell here, I grid cell, multiplied by the surface area of that grid cell, like let us denote it AI. Surface infinitesimally small surface area of the ice cell. Then now this cell now became this cell here. So it still has the same f or value of omega. So function of omega has also the same value as before, and surface area is the same. So if you break down the old integral over initial situation and new integral over the new situation, if you break down into sum over such new grid here, you can see that all the terms in the sum will remain unchanged. So from here you can conclude that integral f of omega d square r is constant from this consideration. Because each of the grid cells preserves area and preserves value of omega, so the integral remains the same. And we have here a functional freedom. We can take arbitrary function f of one real variable omega. So that's why we can say that we have infinitely many conservation laws, because, well, this here is one conservation law. This one here is one conservation law, but additional we have integral of something is constant, but here we have infinitely many integration conservation laws, because we have functional freedom, which function we choose for this conservation law here. And in particular, if we take if f of omega is omega squared, we obtain a conservation law which is called entropy. So, Raido, is it okay?
Yeah, it's okay now.
And yeah, we use this to show stability. So, what is clear how the stability becomes from y it becomes?
Could we go back to the previous slide for a second?
Here, yeah.
Yes, thank you. My connection failed, so I didn't get to write everything. Okay,
Yeah.
thank you.
All right. And then, yeah, in order to show that the cylindrical vortex is stable, so we used generalized criteria for stability based on conservation laws. That for a system to be stable, you need to have conditional extremum of one of the conservation laws by fixed conservation laws of all the other conservation laws. So was that more or less clear from where it comes? I can show you one, and that was like in order to make introduction. We discussed the stability of a rotation of a solid body. Did you was that part more or less clear?
Not for me exactly. I would like to hear more about that.
Okay. Let me first just a moment. Let me try to find the video, which is nice to see actually. Just a moment. Yeah. Now I share another screen. Over here. So this conditional extreme part is actually written down also here. So IPHU 2012, and you can browse here. I can also, if you want, I can copy paste this into open board screens. I am going to send you open board screens as well later. This is written down more or less nicely, I think. I hope. And but then let us see. There is, I think, one link which we can try to open. A video here. Let us see if this is this video is a dead link. But maybe if we can make a search for this file. Yeah, it's maybe you can get it from the web archive. Yeah, internet is doesn't have that either. Too bad. Okay, basically what it was video made on the International Space Station. It might be under some other name. It was a nice video, so just pity it is no longer available. Just a moment.
Is it like the video about like the bolt in like that is spinning in one way, then it switches direction in the other way?
Yeah, you put it different way rotating, and then.
I found it on YouTube. I can share it maybe.
Oh, very good. Please do.
Okay.
Because originally I tried to link the original source, which was Meta, yeah. So, but then now it became dead. The link. All right.
I put it in chat. In the Zoom chat.
Let me see. This is not exactly the same, but maybe he was rotating a book. ESS. I'm pretty sure it's somewhere available, but gyroscope, maybe something. Rotating solid bodies, this microgravity. Oh, what this one, yeah. This is exactly what I wanted to show you. Do you see it? Is this screen sharing working?
Yes.
Okay, let us have a look. So you take a book and put it rotating, and it. Let me mute it. Yeah. So you have stable and unstable rotation. So I can go back once again. So right now, the rotation axis is such that the moment of inertia relative to the rotation axis is minimal because the distance, angular, the moment of inertia is sum over mr square. And now, if you put it rotating such way that, as is shown right now, the distance of the points of the book are as close as possible to the rotation axis. Now this is stable. And then you put it rotating next so that the rotation moment of inertia is maximal, this one here, and now it is also stable. And then you put it rotating, so the third possibility, and it is no longer stable. You put it rotating, and it starts more or less like apparently chaotically rotating. So you have stability when it is one way, and unstable when it is other way. And yeah, here. More videos here, what bubbles make it more interesting and so on. But the main point was the demo with the book. And then what I told you last time during the lecture was that the reason for this behavior that two cases are stable and one is unstable. The easiest way to show it is using exactly that generalized stability theorem. Raido, you have been studying at Tartu University, right?
Yes.
During your undergraduate as well. I was also back in 1982. I was also first year of studies. I was in Tartu, and then we did have this experiment during our mechanics lectures. So did you have it or maybe not?
Experiment, maybe.
Yeah. So demo during lecture.
Yeah, we had some demos.
Yeah, you had the same demo, yeah, but you probably were not given the proof of it, or were you?
Don't remember really well.
Yeah, most of the proofs are quite cumbersome mathematically, but the easiest way to show it is by noticing the following. So that if we take a kinetic total energy for free rotating body, kinetic energy is full energy is just a kinetic energy. E is equal to T because we have no potential energy, but this guy here is, we know that this is moment of the angular momentum divided by 2 times I, where I is axis of inertia of moment of inertia relative to the current or rotation axis. But I actually, this depends on the axis X. And then on the other hand, we have also angular momentum is conserved if we have free rotation, free rotating body. L is constant. And then if we now consider conditional extremum of E, conditional extremum of E by fixed L. Then we can see that it depends only on what is in the denominator, only on Ix. So if Ix takes maximal value, then E is minimal. And if Ix takes minimal value, then E is maximal. And a generalized condition for stability is which we have minimum and maximum both wide. So if energy is either minimal or maximal, we have if we have conditional maximum, then we have still stability. And this is exactly what you saw in the video. So as long as Ix is minimal, it is stable. As long as Ix is maximal, it is stable. But in one case, it's because of energy has conditional minimum. In another case, because it has conditional maximum. But intermediate case with intermediate I, this is not stable because you don't have extremum. And the reason why you are used to having you are used to know that system is stable if potential energy V has minimum. This is because NE equals V plus T, and T has in equilibrium V equals to 0, speed is 0, which means that T is minimal. So kinetic energy usually for the equilibrium has always minimum, and so so you can have only minimum local minimum of E. So you can have only the minimum of E. So you need to have a minimum of one of the conserved quantities, which is energy in this case. And because T has a minimum and E is T plus T, so the minimum of E will happen if V has minimum. So V must have a minimum. And this is as long we speak about absolute extrema. But if we speak about conditional extrema, this is no longer necessarily the case, as you saw in the case of rotating book. In that case, if you fix consider conditional extremum by fixed angular momentums, then of course there is no longer need for the energy to be kinetic energy to be zero and to have minimum. So you can have the both possibilities. Now, is it clear more or less? Zoraida, how you feel about it?
Might watch over this part later, but we might go on now.
What about the rest?
For me, it didn't really clear it up. I don't really get it.
Okay. All right. And so, so we have, you can read indeed from that link, which is over there, if you want to opportunity to think more about it. And so let us move on. And now we have a particular application for showing that the circular vortex, for instance, the same vortex which we had for homework last time, that this vortex is stable. So what might happen? It might happen that you have a vortex, and which is circular initially, but then maybe it will evolve into some ellipse or whatever, who knows. The circular shape might be unstable. Is the circular shape stable? Basically, are tornadoes stable? Well, we know from the experiments that they are more or less stable, because tornado is basically a two-dimensional vortex. Exactly, you have inside tornado you have a vorticity, outside you won't have. A velocity goes down like 1 divided by outside tornado. Outside a tornado, V is inversely proportional to distance, as we saw from the homework. So the question is if this shape is stable, and if it is, how to prove it? And the answer is that the way we are showing it is we show that the tornado has conditional maximum of energy by fixed vorticity. So answer is it is stable because it has a maximal energy by fixed vorticity. Conditional extremum. And how we show it is that we have certain initial tornado shape, so what is vortex shape. So inside we have a circular area, we have omega equals to omega is different from 0. Outside omega is 0. And then we consider certain perturbation of the shape. If we have perturbation of the shape, let us say that vorticity from somewhere here becomes to here. So we have surface because we know that omega vorticity is transported only as in terms of Lagrangian transport. So d omega full derivative or Lagrangian derivative is 0. So a piece with certain omega is transported to somewhere else. This is the only way for the vortex to evolve. Surface area with the region where omega is constant must remain the same because of this equation, and so only the shape can evolve. But now, if you say consider this evolution, you have this. It is the same way as if you added here certain negative omega here. You add certain minus omega here in this region, and here you have added some positive vorticity here. And now you remember how you were able to calculate the energy. The total energy was one way. We can write it like that. Energy is integral v squared divided by 2. We assume rho equal to 1. V squared d square r. This is one way of calculating it. But then the other way is by using the potential. So let us recall what we have for electric field. For electric field, we had something like that. We can calculate the full energy of electric field in two different ways. One is because E is electric field strength, I used a W for energy. The W total energy is maybe I change here also for W is integral E squared divided by 2 epsilon naught and d square r. This is one way of calculating it, but the other way of calculating it is W is sum over all the or maybe yeah, we can write it in as in terms of sum as Qi also charged, yes, Qi Qj divided by distance between them I Rij and multiplied by 1 divided by 4 pi epsilon naught. And we take some such sum that I is over such pairs that I is bigger than j. Does this expression here need clarifications, or is this clear to everyone?
What was the question?
Is this clear what I wrote here, how it comes and what it is?
Not really.
So at the second row, or last row, I am calculating energy of electric field. There are two ways of calculating it. One as integral over the energy density over space. Energy density is okay. Let me change it to Q, R cube. So one way is to calculate it over the electric field energy density, which is E squared divided by 2 epsilon naught, and I multiply energy density by volume and integrate, and I obtain the full energy. The other way is calculating in such a way that I consider electrostatic repulsion energy or attraction energy of the charges. And so I imagine I start removing charges from our system to infinity. I take first charge, and then first charge interacts with all the other charges. So if I take Q1 and Qi and divide by R1I, then I obtain the, let me write it down also. So Q1, first charge multiplied by Qi, divided by distance between first charge and ith charge. Gives and 1 divided by 4 epsilon naught. This gives us the energy of interaction of first and ith charge. So I remove first charge, and in order to find which work is done by that, I need to sum over all the i's of Qi, Q1, Qi divided by R1j, 1i. But and then I next remove the second charge, but now I don't have a first charge. Now I need to consider those j's which are yeah, let me just which make those. Let us reverse it. Now I need to take those j's which are, no, it was still okay that way, I think. So I is bigger than j. So first we started with I equals 1, and we took all j equals to 1. This corresponds to j equals to 1. And then we take j equals to 2, but now first charge is already removed. So now we need to take only over those i's which are bigger than 1. And then so on and so on. So in general case, we take those i's which are bigger than j. We sum over all CPS, and then we obtain interaction energy of all CPS. Two ways of calculating energy of electric field. Is this okay? Kaspar, did it become clear?
Yeah, you're basically summing over all the charged interactions.
Yeah. So there are two ways of calculating either electric field in terms of electric field or charges. And now we are going to do the same for the vorticity. And this sum over here, this can be also written as follows. This can be written as this equals to, in terms of integral. Before going to integral, let me write it like that. This equals 1/2 due to symmetry. I can either sum over all i's that are bigger than j, or we can sum over all CPS, but then I am calculating them twice. When I is bigger than j and when j is bigger than I. So if I sum over all CPS, I calculate each of the terms in the first expression twice, so that now my sum becomes needs to have 1/2 before. Qi, Qj divided by Rij, and 1 divided by 4 pi epsilon naught. And now this can be written already in terms of integral. 1/2 and integral now if we fix here I, and then the sum of, okay, maybe I put here one more step so it is easier to follow. One more step here between my derivation. So this sum here now, this can be written as a double sum. So this becomes now 1/2 sum over i's qi, and then sum over j's, and here we have qj divided by rij, 1 divided by 4 pi epsilon naught. And then this guy over here, this here is potential of all the other charges created at the position of the ice charge. Potential at the position of ice charge, if you look at it. Qj divided by Rij gives you the potential of the j's charge at the position of I, and if you sum over j's, then you obtain the total potential which is over there. So this thing here now can be written like 1/2 integral of qi of phi I dq. I can drop now I index I. Sorry. I drop index I. So I sum over qi in terms of integrals. This becomes integral over dq. So this becomes phi at the position of the charge multiplied by dq, and I need to integrate over all the charges. And this is how I do it in terms of charges. But if I repeat the same thing in terms of a similar thing in terms of vorticity, then we have a similar expression. But before that, probably we need a little bit to compare things. So for equation for vorticity, we have for electric field, we have an expression like that. Laplacian of phi electrical potential is equal to rho divided by epsilon naught, where rho is electric charge density. And rho d cube r is dq. The dq which goes into the integral. This goes into here, into this integral here. This dq. Now, if we write the same thing for the similar things for the vorticity, then we have now, what was it? Vorticity was curl of V, so that so we had omega is curl of V, and so but V is, we had stream function. So if we plug in stream function, then it becomes Laplacian of stream function. So for omega and stream function have the same equation. Omega in terms of stream function has the same expression as the charges. And so instead of calculating kinetic energy in this way, we can actually calculate kinetic energy in terms of charge interaction. So using this similarity, we can now write that this is something like that. 1/2 and integral stream function and omega and d square r. Okay. And now it is quite easy already to figure out what happens with the change of energy during our perturbation. So we sum over all the dr surface areas, and if we displace certain part of vorticity to somewhere else, so change in the psi will become very small. We can also show that this is very small. And then what remains is so variation of energy. It will become vorticity, total vorticity, which was transferred over. So this is omega d square r. How much amount of vorticity multiplied by how much changed the how much is different stream function between this position and that position. So multiplied by stream function value difference psi1 minus psi2. And then a stream function in the red position is bigger than so if we have here psi 2 psi 1, yes, psi 1 and psi 2, then because psi 2 is bigger than psi 1, so our change of energy was negative. And so it was arbitrary perturbation, and we conclude that for arbitrary perturbation, energy change is negative. So it means that our initial situation has corresponds to a conditional maximum of the energy. Is more or less clear? You can also think about like each region where you have omega different from 0. So you can just substitute this with electrical problem. So everywhere where you have omega, you replace it with electrical charge density rho. And you can equally just consider how much will change electrostatic energy. Energy between interaction of charges. And then you can easily see that the cylindrical geometry corresponds to maximal energy, because if you displace charge from inside to outside, outside then the potential is smaller, so inside is bigger. So whichever change you make, you displace charge from a bigger potential to smaller potential. So you decrease the energy. And yeah, to be very precise, you would also need to consider the interaction. So if we look at this this expression here for the energy of charges, then you would total energy involves charge multiplied. So we have two new charges appearing. We have here minus charge and here plus charge appearing. And we ask how much will change overall energy. So this comes from interaction of this new charge here, which also has the charges, this charge, which also has the charges, and this is this thing here, what I have. But then, strictly speaking, there are also interaction of this charge and that charge. But we assume that these charges are very small. So this is infinitesimally small, this is infinitesimally small. So product of them is infinitesimal squared. But this, if this multiplied by potential here, this we have only one is infinitesimally small. So here the interaction of this minus and this plus, this can be neglected because this is infinitesimally small square. So yeah, how is it? Did it become clearer?
No, not really. Maybe the transition, for me, the transition from like the electricity side to vortex is strange.
Okay. Just like it is isomorphism, we have the same equation for vorticity and for electric field, and just we match one to the other, nothing else. We have the same Laplace equation for phi as we have for the stream function psi. And yeah, you can actually now how to show that if you are like inconvinced, like I was telling you, just you can take this and this equal to that. Actually, you can show it also mathematically using the integral theorems what you have over there. But I think it's if I were going to do it, it would be like another half an hour at least. So maybe it will be a waste of time. Just so you know that this equality here can be shown also mathematically using integral theorems. So I gave you it's like from physics, you know, but this can be also shown, can be proved, can be also proved using integral theorem. You know the integral theorems. One is Ampere's integral theorem, the other is Stokes integral theorem, which corresponds to Ampere's circular theorem, and the other is Gauss theorem. Using integral theorems and Maxwell equation, and this. And this. So integral theorems together with this Laplace equation can be used to show this equality what we were using. So Raido, is it clear, more or less?
I have some idea.
Yeah, if you have interest and try playing, you can try showing and working on it. But like the basic idea is as I told you. So you instead of considering integral v square dr, you go to expression of the interaction energy written as that one here. Stream function multiple omega d square r is same as this one here over here. So these two are equal to each other. Equal. Again, you can use it also mathematically using the integral theorem and this expression here. No problem. And then with this expression at hand, we can already easily show that any perturbation what we make to the cylindrical vortex will give rise to a decrease of the total energy, to a decrease of kinetic energy. So, which means that actually, yes, this vortex is stable as long as we don't have dissipation. But with dissipation, things might change. So if we introduce certain viscosity, so it's no longer sure what happens then, because we assume that energy is conserved. But if energy is not conserved, then there is a possibility for system to become unstable, and these are called dissipative instability. So a situation when a dissipationless system is stable, but any dissipation will give rise to instability. For instance, if I go back to the book, throwing book and rotating. So again, if you have no dissipation, then we have a largest axis for moment of inertia is stable, smallest moment of inertia is stable. But if you introduce, say that, okay, there may be some friction, in that case, it might be that actually the case when you have conditional maximum of energy, this becomes unstable because energy will start decreasing due to dissipation. But that case, when you had minimum of energy, then dissipation will no longer be able to lead out from the minimum still, because it makes it even smaller, right? So probably there is, if you introduce dissipation for the rotating book, one of the previously stable cases might become unstable. So what we call is dissipative instability. Okay, Raido, bye. All right, already left. So now, what else? Next, we moved on to Rayleigh-Taylor instability and Kelvin-Helmholtz instability. So how do you feel about those? Do we need to explain that some more?
Yeah, maybe we could go over them as well.
But I guess it's like going through everything. Maybe just what is important. What is important? Important is just what are these instabilities about. So can someone of you summarize what is Rayleigh-Taylor instability? Maybe Siim, or what is Rayleigh-Taylor instability?
I don't have a good answer at the moment.
Kaspar.
I didn't make it that far in the video.
Once again.
I didn't make it that far into the video.
Ah, you didn't make it that far in the video, Krislin?
I don't know exactly the definition, but something that it's like instability between two flows or two fluids or something like that.
All right, so maybe we'll do that way, that we are not going to the maths right now, because the maths is the lecture recordings and the lecture notes. Maybe we just make some summary, what are these things about, and then you look more into maths over there. And so, let us add here one more page. And we have then Rayleigh-Taylor instability. Rayleigh. So this happens when you have heavy liquid on top of a light liquid. Row 1. And here you have row 2. Why doesn't it just now? So that row 1 is bigger than row 2. Then you have instability. Now, it's quite clear that always heavy liquid is at the bottom, right? So if you like take water and oil has smaller density, so it is stable when light is on top of heavy and unstable otherwise. And now, well, it is quite clear if we talked about those stability conditions, then here it is, we can still use the same classical method of looking at the potential energy, and it is quite clear that if we disturb the surface somehow, then take some perturbation of the interface line here. So let us say this becomes now something like that. Then we have energy decreasing because we have effectively some mass is moved from top to bottom. Some mass goes that way. Some mass goes down, which means that energy is decreased. Potential energy is decreased. So it means that energy had there was no minimum. Energy potential energy was not minimal. Was not minimal. And because total energy is potential plus kinetic, so we don't have extremum and we won't have stability. It is quite clear. But now this is one part. The other part is that you might ask how fast instability develops. And usually when you study instabilities, then this is exactly what you do. You calculate instability increments. For instance, simple situation like that. You take pencil and you put it standing on its tip, and you ask how fast will, you know that it is unstable, but you ask how fast will the instability develop. You assume that there is a small angle by which is declined, so small angle alpha. New position of the pencil is like that, and then you have a torque applied to the center of mass. If the length of the pencil or bar is L, then we have torque equals to equals to mg and L divided by 2 multiplied by small angle alpha is L divided by 2 multiplied by alpha is the arm of the force, and this must be equal to moment of inertia I, but and multiplied by phi double alpha double dot. Alpha double dot, where I equals to 1 divided by 3 and ml squared. And then we have equation alpha double dot equals m cancels away. You have 3 over 2 g divided by L and multiplied by alpha. And then the solution here is alpha equals to 1 integration constant e to the power of square root of 3g divided by 2L multiplied by t and plus c2 e to the power of minus 3g over 2L times t. And now, because we had arbitrary initial position, so there is no way that so C1 and C2 are to be determined from the initial conditions, but there is no way that one of them is exactly 0. So none of C1 and C2 are zeros. It just is physically impossible to achieve that it's exactly 0. So C1, C2, they are not zeros. And so if we wait for a long time, so second term goes to 0 and remains only the first one. So alpha will tend to exponentially increasing solution C1 e to the power of 3g divided by 2L times t. And then this guy over here, we can denote it as in terms of gamma, is C1 e gamma t. So this gamma is called gamma is instability increment. And then you can just say that because now the solution will grow exponentially with characteristic time 1 divided by gamma, characteristic time tau is 1 divided by gamma. So instability will evolve in characteristic time equal to 2L divided by 3G. And so estimating so that instability increment makes it possible to estimate how fast the instability will evolve. How long time do you need to consider it? And now what the next lecture, this second part of the lecture is about finding characteristic time or instability increment for Rayleigh-Taylor instability and for the Kelvin-Helmholtz instability. Now this bar, falling bar stuff, is it clear more or less?
So just to summarize, the instability is caused by mass shift, right?
Once again?
The instability, this Rayleigh-Taylor instability is caused by the shift of mass.
Yeah, so heavy tries to get lower, displacing out light, and that's how it happens.
And if the angle of displacement increases, then the instability increases exponentially.
No. Now you are a little bit confusing. So, falling pencil was completely different problem, unrelated in a sense to the Rayleigh-Taylor instability. So I was saying that we have unstable situation when you have a heavy liquid on top of light, and the next task would be to determine the instability increment. So that if we have instability, you usually want to determine the instability increment. And then I took another simpler like a problem which is intuitively easier to imagine. Intuitively easy to imagine problem is a falling pencil, a falling bar. You put a bar standing on top of one of its ends, and it is unstable. It starts falling, and then we can. What we need to do is to write down a linearized equation. Pay attention that I linearize the equation because actually here would be. For torque should be actually sinus alpha, but I substituted sinus alpha by alpha. I can write it also here. Sinus alpha is approximately alpha, so that's why I wrote here alpha. So I linearize equation of motion and then solve it. And then my solution is going to be a sum of different linear contributions. And if as long as one of them is exponentially growing, then it is unstable. This one here is exponentially decreasing. So this would be fine. This would be not cause instability. But the first one is exponentially growing, and this is what will cause instability. Initial perturbation will grow exponentially in time. This is what is instability. Initial perturbation grows exponentially in time. This is instability. Let me write it down just in case, because I understand it's better to write down important pieces. So if initial perturbation grows exponentially in time, we say it is there is instability. And then as long as one, so if we solve and find at least one, if we find linearized set of equations, and at least one of them, is and at least one of the at least one of the solutions is exponentially growing, the whole system is unstable. So more or less clear. I can write on the next page or so general procedure of finding if a system is stable or not. If you want to find if a system is stable or not. So what you do is first write down all the equations of motion. Linearize this set. Solve it. Okay, solve means actually write characteristics, because this is linear. This is linear. This is a set of linear differential equations which can be solved solved using characteristic equation. You remember what is characteristic equation? Kristlin, do you remember what is characteristic equation?
I like on the top of my head, exact equation, no.
Characteristic equation. What is characteristic equation? So if you have linear equations, constant multipliers, you can always solve it using characteristic equation. Siim-Erik, do you remember what is characteristic equation?
No, I'm not sure.
Okay, let me finish it and then I will go to the explaining what is characteristic equation. For if any of the solutions have positive real part, then system is unstable. Because it corresponds to exponentially growing solution. Now going back, what is characteristic equation? If you go to the previous slide, look here. You have here a differential equation like that here. Okay. Let me frame it. So this is our linearized equation. If we get in terms of those steps, what we were speaking about. So this is a linearized equation we're speaking about now. So this is a linearized equation. And now we solve it by the next step is we write down characteristic equation. Actually, I dropped this part here because I did it in the head by the characteristic equation, what it is. So you look for solution in the form alpha equals E lambda T, so that the equation becomes now, after you cancel out e to the lambda t, then you obtain equation mgl divided by 2 equals I multiplied by lambda squared. This is a characteristic equation. Do you remember the do you start now recalling math analysis somewhat? So characteristic equation is when you substitute second derivative with lambda square, first derivative with lambda. Just function itself, variable itself, you just remove it. Alpha we removed, remains only mgl divided by 2. Alpha double dot we substitute with lambda square. And then we obtain equation for lambda. And now we have lambda equals plus minus square root of mgl divided by 2i. Then because I have plus and minus, one of them has positive real part, the other is negative real part. So one of the solutions, no, why doesn't it write? One of the solutions has a real part larger than 0. Has positive real part, so this plus over here. This plus, if we take plus, we have a real part positive. And now if I go to the next slide, we see that if any of the solutions have positive real part, so we do have one of the solutions which have no real positive real part, so it is unstable. Because then we have this solution here, and this is exponentially growing solution, and that's why. Now, is it fine to everyone?
Is it basically the same thing that we might have done in non-linear dynamics?
quite possibly.
Okay.
Okay, so this is a general approach how you find if a system is unstable or not. And now we need to implement this for the Navier-Stokes equation for the different cases. When we have the first case is Rayleigh-Taylor instability case, the other is Kelvin-Helmholtz instability case, and these are considered in the lecture recordings. And like a rough outline how we did. The Rayleigh-Taylor instability, a rough outline how we do it. So this is somewhat tricky. It's much more tricky than in the case of the falling pencil, because now actually falling pencil has only 1 degree of freedom. But our system has infinitely many degrees of freedom because each of the fluid particles can displace. But what we need to have in order to find the stability, well, actually, you can only perturb the interface. So we can consider what kind of perturbations are possible. And because we know that vorticity is conserved, we cannot, this also needs to be kept in mind. So if we have interface here, and we have heavy liquid on top of light liquid, and initially everything is at rest. And now you remember that whichever way you perturb the fluid, initially we have everywhere vorticity was equal to 0. And if it was initially equal to 0, it remains 0. Vorticity is 0. So if it was 0, it remains equal to 0. But for vorticity is 0, then Laplacian of psi, the string function, is 0. And if Laplacian of psi is 0, then now what next comes to at hand is that well, we say that we have infinitely many ways to disturb this interface. We can give it an arbitrary shape, but we have a linearist equation. And if we have linearist equation, we have superposition principle. Let me write it also like important steps down. Yeah. Our equals linearized. And because of that, our hence superposition principle is valid. So we can, instead of considering all the possible perturbations, we can consider only the a basis, like arbitrary perturbation can be expressed, for instance, as a superposition of Fourier components. Arbitrary perturbation of the interface. For instance, we can describe interface as y equals of f of x, small perturbation. Can be expressed as a superpos of Fourier components. Y equals sum a I sinus there's a k sinus kx. So that you know from the Fourier analysis that any function can be expressed as a sum of Fourier components. And so because we have superposition principle, if we know solution for one of the Fourier components, then we can find also how the system itself behaves, just in terms of superposition of all these perturbations. And so what we need to do is to consider only sinusoidal perturbation. Only sinusoidal, only sinusoidal. Sinusoidal perturbation. Y equals sinus kx. And then what we need to find is the same gamma. We need to find gamma as a function of now wave vector, because you see here we have parameter k. Instability increment as a function of k. And then what happens usually is that the fastest mode wins. The fastest mode wins, which means that what first when you consider the unstable interface, because between heavy and light liquid, what you will first be seeing is the fastest node, which has the biggest gamma, with biggest gamma. This is what you will be seeing in experiment. So if you try to realize the situation was heavy liquid on top of light, then what you'll be seeing first is the fastest mode. Now, if you want to see how it works, you can. There is also such nice thing as Rayleigh plateau instability. Why I'm speaking about Rayleigh plateau instability is because it is much easier to make experiment on Rayleigh plateau instability rather than on Rayleigh Taylor instability. It is easy. It is easy to make experiment with Rayleigh plateau stability. And then there you can see how the fastest mode wins. The fastest mode wins. Well, you can actually make this experiment by yourself at home. You open a tap with water flows out, and then you see how the outflowing water breaks into droplets. This is exactly what the Rayleigh plateau instability is. We might try to see if we can manage to find some nice video on that. And let me share then new share. Ja, pärit asja. That's I think it seems to be good. Over there here. Okay, here you are. Can you see my screen?
Yes.
And then you see that at certain depths, okay, here some explanations, I guess, but yeah, this one here. You can see how it evolves into droplets. Water stream. Now they managed to have it very. What they have is they have very thin tap water. Yeah, sometimes yeah. If you take see where was its initial video? Yeah, some snapshot. Let me see. Ah, yes, this is like here actually a very realistic picture. On the left-hand side on the screen right now, as you can see, if you take a instantaneous snapshot of the water stream which comes from your tap, then you see that it first it is cylindrical, but then some shape changes will happen. Here you have a small neck here, and then actually, but then you have it ends up of having certain wavelengths, so to say, along the stream, and so the distance between the droplets is more or less the same everywhere, and this corresponds to the fastest instability mode of this Rayleigh plateau. That now, if you take a very here it appears that if you take very long wavelengths for the perturbation, instability is rather slow. On the other hand, if very short wavelengths, they are not even unstable because you have capillary effect, which prevents like perturbations to small to appear. So there is a certain wavelengths which has the biggest increment, and that's what you see in the experiment. And yeah, you have here also probably you can find also some experiments on the Rayleigh-Taylor, but this instability is usually much more difficult to do because it is difficult to obtain initial situation when you have heavy on top. Okay, here they seem to somehow to obtain it. But on the other hand, it's usually when you heat from the bottom, then you have also okay. The previous one might have been better. Yeah. Okay, this is already deeply a nonlinear stage of instability. So usually instability start off with stable which like linear, and then once the perturbation grows so big that linear approximation is no longer valid, then it becomes nonlinear. So linear is when you have sinusoidal shape, but here is already strongly nonlinear, as you can see. So if we can, I don't know if we take at the very beginning, can we see something like what is more or less like sinusoidal first? Yeah, maybe here you can think about these like small sinusoids, right? They start off situations, perturbation is so small that linear approximation is valid. And then as time goes on, the perturbation grows, and then no longer linear approximation is valid. So you start already seeing like strong nonlinear solutions over here. Okay, more or less clear what I was trying to tell you. Yeah. So this is what you need to do. You need to more or less the same recipe what was written here previously remains valid. So write down a linear also equation of motion, but now one more step is added. Consider Fourier component.
We can't see your screen.
Oh, sorry, yeah. Sorry, I go back to open board. All right. So the same step what I here remain valid, but one more step will be added, and this is here into here. Consider a Fourier mode. Consider sinusoidal perturbation. Perturbation e-test Fourier mode. Mode of wave vector k, and then those the same. And now, yeah, coming back to Rayleigh-Taylor, so we have Laplacian psi is 0, and from that Laplacian psi, what actually you do if we consider it sinusoidal in x. Now we are looking for solutions. We look for solutions which are sinusoidal in x. Psi equals, but it can depend on y. Psi of y multiplied by sinus kx. And if we plug this into here, we can see that the only way to have it is psi equal to e to the power of plus or minus ky multiplied by sinus kx. So it is exponential in vertical direction and sinusoidal in horizontal direction. So if you plug into here, you can see that actually this satisfies the Laplace psi equal to 0. Because sinus kx gives you, if you take second derivative, gives you minus k square, and if you exponent in y, partial derivative in y direction gives you plus k square. So plus k square and minus k square cancel out. So you can see that the solution of this Laplace psi equal to 0 is e plus minus ky sinus kx. But then again, you can see that the only you cannot have like infinitely growing solution. So your solution must be exponentially decreasing into the depths here and into the depths here. So here is e minus ky, and here, yeah, if y coordinate is that way, and here is e to the power. Let me write the modulus of e minus ka. So e minus ky. So it needs to be always decreasing exponentially to the depths, either upwards or downwards. And so this is how psi Fourier mode of psi is. And the next thing is that you need to consider like you have now two solutions. One is up and the other is down, and then now you need to join them. Because you also know that if blue particle goes up, yellow particles here need to also go up. So we have one solution upwards, upper part, another solution we have in lower part, and you need to tailor them. You need to tailor tailor two solutions, which is one is at y is bigger than 0 and at y is smaller than 0. If you tailor it, that's from where you obtain the Rayleigh-Taylor instability. And if you do it, you obtain something like that. Gamma equals. Now you can more or less already figure it out from the dimensional considerations that it will be something like gamma times k, square root of a gamma times k, and then there is something like rho 1 minus rho 2. Rho 2, here is rho 1, here is rho 2. And divided by rho 1 plus rho 2, something like that. So this is exponent what you obtain for instability, and you can see that as long as rho 1 is larger than rho 2, gamma is positive, and you have instability. If it is other way around, you have imaginary gamma. Imaginary gamma recalls that it was solution in the form of E gamma t. E gamma t. Imaginary gamma is sinusoidal fluctuation actually. So if the square root is negative, you won't have exponential growth, but you have oscillation, you have wave. So this what you obtain is actually deep water waves, how water run on deep water. So I can write it also on the next slide as well. So what we conclude is if rho 1 is bigger than rho 2, then we have E gamma t, gamma equals square root of gk rho 1 minus rho 2 divided by rho 1 plus rho 2, and this is unstable, Rayleigh-Taylor instability. Now, if we have rho 2 bigger than rho 1, then we have sinus omega t. Omega is now the same as gamma, but with negative reverse sign under the square root. Square root of gk rho 2 minus rho 1 divided by rho 1 plus rho 2. And these are deep water waves. Okay. How is it more or less okay? So these are like what we did right now was like a general framework how we approach the problem and a conclusion. So some conclusion what you're supposed to know more or less. That we have instability. You can already from dimensional considerations write down some gamma, which is needs to be 1 over second. If you combine from G and K from the wave vector expression, you can see that the only way is to have square root of GK, and then yeah, then there is a ratio of those rho 1 minus rho 2 divided by rho 1 plus rho 2. And now if you look at the expression of gamma, I told you that the fastest mode wins, but here the bigger the K, the bigger gamma. Gamma increases with K. With K. So what is another question is what is the fastest mode now? Is it infinite K? No, actually, we neglected capillary effects. So if we capillary effects, so if we introduce also surface tension, then actually surface tension will stop the instability. So if we also include surface tension sigma, then there will be K optimal by so that gamma as a function of K has maximum at K optimal. So this is the fastest mode. So as long as you ignore surface tension, you say that the shorter the perturbation wavelength is, the faster the mode evolves. But if you introduce surface tension, then it is no longer the case. And you have something like half a centimeter, a few millimeters is the for water. For water, K 1 divided by K 1 divided by k optimal, around a few millimeters. Which corresponds to the fastest mode. Now, was it more or less clear what I was telling you? I tried to keep it as simple as possible. Kaspar.
Yeah, it's a bit hard to focus this late. I mean, the modes were a bit confusing, but I think the sinus stuff was okay.
Just you need to be used to the terms which we use. So mode is like one Fourier component. We consider one sinusoidal solution is a mode. What we call mode is one sinusoidal solution. This is just the term you usually used in this context. If you have linear equation, you have superposition principle, you can decompose solution into different modes, Fourier modes. So Fourier components, so Fourier modes. That's a term used. Nothing difficult. So one, again, the framework of the approach, how we do it, is represented here, written more or less down step by step. And the conclusion is that we do have expression for the instability exponent gamma, and then the fastest mode, in order to find the fastest mode, then you also need to include surface tension, and you have certain wavelengths for the perturbation, which you will see in real life if you make experiment. As for Rayleigh-Taylor instability, actually, there is a nice lamp which is, I think the name of the lamp is plasma rocket or something like that. It's like something like wax is at the bottom, and then lamp is heating it, and it is made colored into with paint into some colors, and then as the wax becomes warmer, the density will decrease, and at certain point it becomes unstable. And then the bubble starts raising up, and it's very nice to look, actually. I don't know if you have seen that, but you can keep in mind that very nice, nice physical toy. Krislin, how is it? More or less clear?
More or less, yes.
Okay. So if you feel that math is some here there difficult, just try to keep so that you understand the, like conclusions and like initial conditions and conclusions, those qualitative things. You can skip somewhat math. Yeah. Okay, so guys, how are you? Our time is 2 hours, is more or less now over. So shall we finish? Or?
We don't have any more questions.
All right, so please consult again lecture, and then I hope you can. Oh yeah, homework.
I don't think anyone solved the GPO homework. So
all right, okay. So let us keep that GPO as homework, and no homework for next time then. So so that you can you will manage to finish that one. Okay, then until next time, next week.
bye.
Bye.
Bye.